Tolga sen çıkıyorsun. Hiçbir yerde oturmuyor. Boş bir yerde oturmuyor.
Ya da teke falan düşebilir. Çünkü orada şey
Şöyle yapayım. Görünmese de devam edelim. Şöyle olsun. Şu ne kaldı böyle. Onu da şöyle haplayayım. Ha? Evet. Sen bir kontrolünü yap. Hareket ediyorum. Yok, şey yerinde duruyor. Pointer var. Şey mi? Dur. Hayır. Biraz denesen. Yok, yanlış şey yapıyorsun. Tamam. O zaman başlayalım. Welcome everyone. We have today Özge Keskin, who is a PhD student at Sabancı University, and they had a very nice paper out a month ago, I guess, is it? Anyway, so we want to hear more. Thank you very much for coming, and go ahead. Thanks.
Hi everyone, welcome. Thanks for being here. Today I will talk about our latest study, which is concise spectrotemporal studies of magma SGR 1935 burst. So far we have observed lots of activities from various magnetites, and once a magnetite becomes first active, we usually observe successive and various types of emissions, and it allows us to study the physics behind, and spectral analysis helps us a lot in this sense. And the spectral studies so far has been shown that there is a significant spectral evolution even during short magnetite bursts. And time-zone spectroscopy help us to reveal the spectral evolution of the burst. In regular time-zone spectroscopy, however, time meaning for the extraction of spectra is arbitrary. So we divide the burst into time segments either based on its signal-to-noise ratio or to contain sufficient number of background subtracted counts to ensure reliable statistics. So if we divide the burst into too many pieces, then in each piece we will not have enough data and statistics to perform our analysis. But on the other hand, if we divide only a few pieces, then we will lose the spectral information. So therefore, we need a balance between these two edges, but in any case, the result will depend on the initial time being, because we do not take the spectral changes into account, and this leads us, so this way, it's not possible to extract a true spectral evolution of the burst emissions in the sense. And our question was, can we perform a more foresighted time-zone spectroscopy? And to do that, we followed a two-step approach. The first one is overlapping time-zone spectroscopy, with which we can define overlapping time segments and obtain the spectral parameters. So here on the top figure, here the x-axis is time, and the red horizontal bars shows each time segment. And please see how they overlap in time. And by doing so, we can keep each time segment long enough so that we can ensure reliable statistics. But also, since these time segments overlap, we will have the continuous spectral information in the sense. And this will allow us to take the spectral changes into account. By using the results of the first step, we can follow a second spectral analysis by taking these changes, spectral changes, and extract a more true spectral evolution of the overall emissions in the sense. And to do that, we choose the clustering approach, because with clustering here in the bottom figure, we see that the spectral parameter of overlapping time segments is an illustration. And with clustering, we are able to combine the similar parameters and minimize the differences between the clusters while maximizing the differences between the clusters. And then we can take spectra for each cluster and analyze these and obtain our final result.
Question.
Yeah.
You keep saying clustering. And how many spectra are in each cluster? Is that uniform? Or have you taken maybe like 20 spectra somewhere and clustered them, like 5 spectra somewhere, clustered them?
So I will explain that in detail. So these are the very basics. Just to show that, so we are taking a first step to obtain the spectral changes, and then cluster the similar values via clustering. I will explain the details. Yes, the number of overlapping time segments can change in each cluster, so it's depending on the evolution. So with clustering approach, we are able to divide the burst whenever it's necessary. I mean, if there is an evolution, we start to divide, but if they are similar, we don't need to divide that region of the burst because we don't see any evolution. And our one of the motivations is to understand the underlying physical mechanisms of these burst emissions, and the spectral analysis is important because each model that we use in our analysis comes with its own explanation. So far, there are 2 models that represent the magnetar burst spectra well. The first one is the summation of 2 black bodies, BB plus BB model, which supports thermal radiation. And the second one is a power law with a high energy exponential cutoff, which we call Comte model in short. And this model suggests synchrotron-like non-thermal radiation. And there is also another model proposed by Yamasaki et al., a modified black body with resonance cyclotron scattering. I will explain the model in a minute, but before that, please see how these 3 photon models, each of which shown with a different color, represent the magnetar burst spectra band. And this MBBRCS model assumes a black body near the neutron star crust, and it's modified by taking the high magnetic fields of magnetars into account. And the photons emitted this burst active region near the crust escape to infinity after just one scattering by the magnetospheric charges. And so far, testing the model with the energetic layers of SGR 1900 resulted in a good agreement with the spectra of intermediate flares, but not with the giant flare that was observed in 1998. And our question was, how about the short magnetar bursts? And we systematically applied this burst to magnetized spectra at this scale for the first time. And to do that, we created a table model spec. So if you are interested, you can download the model and apply to your data by using the link in the paper. And we studied SGR 1935 bursts since it's the most one of the most prolific transient magnetites ever observed, including many short bursts. And it emitted an intermediate period in 2015 and a burst forest in 2020. And maybe the most importantly, it emitted the first galactic phase radio burst associated with an X-ray burst. And this may be an indication that maybe the FRBs observed in distant galaxies may arise from the magnetites of dead galaxies. And for our burst sample, we choose the brightest SGR 1935 bursts observed with gamma ray burst monitor on board primary gamma ray space telescope. And we use this continuous time take event data of time GBM since it provides the finest time and energy resolution. Our energy resolution is in between 8 kV to 200 kV with 4 milliseconds minimum time resolution. And we use the data collected with the 3 brightest sodium iodide detectors with detector to source angle less than 60 degrees. And for the duration of the burst, we use a Bayesian log approach. And for the extraction of spectra of overlapping time segments, for each segment, we require an overlap with the previous one by 80% so that we can obtain the continuous spectral information. And we also required a minimum of 1,200 background subtracted burst counts to ensure reliable statistics. And in the end, for the first stage of spectroscopy, overlapping time loss spectroscopy, we obtained more than 1,000 overlapping time segments and spectra. And in the spectroscopy, we fit the spectrum of each overlapping time segments in the spectrum using Kester statistics with 3 different photon models that we discussed at the beginning. BB plus BB model, NBB RCS model, and quantum models. And after fitting process, we need to, for each time segment, we have 3 different photon model fits. So we need to determine which one is statistically preferred or which one is better in sense. And for this, we employed Bayesian information criteria. Yes.
So just about this Bayesian information criteria you use to only to sort of test the improvement by a model. How different is it from F-test? That's an older version of using chi-square. Does it improve upon F-test, or is there another version that does a similar thing? Simple question.
Yeah, this is we have the total data to perform our spectral analysis, and therefore we use Kester statistics. And I think in the statistics you say chi-square, right? So I think this is using the
so since you're using CSAT, you are inclined to use the big number
this is based on
test or whatever it is. But I just asked how different that is. So since you have 1,200 photons in each of your spectrum, right? Like that's not so little.
Yes.
I wonder if this improves upon a chi-square analysis.
Yes.
Have you checked that?
Yeah. So
this is just a technical thing. It's not just. I wonder.
To use chi-square, yes, we have lots of photons in each time segment, but we have also very energy channels. So in each of them, to apply Gaussian or to apply chi-square statistics, so in each of them, we need to have some specific number of photons to use it. But here, for each channel, energy channel, the number of photons are changing. So it's not allowing us to use it to chi-square. I mean, the C-stat is more appropriate for our data.
But you have not tested how well the others describe your spectrum.
Yes. So to decide the improvement of the model fits, we employed Bayesian information criteria, and we calculated the Bayesian information, the BIC value as follows. The C-stat, the coming from the fit statistics, plus number of model parameters times the natural logarithm of the number of data points. And for each time segment, by comparing BIC values, we can decide a statistically preferred model or models. And if the BIC value is greater than 10, we pick the model with the lower BIC value. And if the BIC value is less than 10, then this means that both fits are comparable and both models are equally preferable. So this 10 is coming from the bias factor. It provides us the 99% confidence level. And at the end of the first step of the spectroscopy, we found that the cone model is preferred by nearly all time segments, but a significant portion of the spectra also prefers the thermal models as well. And before continuing the second step of the spectroscopy, clustering-based kind of spectroscopy, for clustering, we choose the EP parameter as reference because, as we said, the cone model is preferred by nearly all time segments, and the second parameter of the model, namely photon index, does not vary significantly within the individual events. And for clustering, we used K-means clustering approach by using the midpoints of the overlapping time segments and their corresponding EP values. So in here, so in this figure, we have the EP values of the overlapping time segments. The gray dotted lines show the light curve, and the dark gray crosses show the EP values. And via K-means clustering, we are able to combine the similar EP values and maximize the differences between the clusters. And these overlapping time segments yield spectrally distinctive clusters. Here, each color shows a cluster. And by following this clustering, we can extract spectra for each cluster. And we analyze the clustered spectra and we can obtain our final results, which are independent of initial timing as much as possible, and we can extract a more true spectral evolution in the sense. And the bottom picture shows the same burst again, but this time it shows the KT parameter evolution of the thermal models. And the thick data points at the top and bottom show the high KT and low KT parameters of the BB plus BB model. And the thin data points with circles show the KT parameter evolution of the NBB RCS model. So,
sorry, have you put, when you say KT, have you put fit on a, so there is, for example, the green ones is BB plus BB and CONT. Is that CONT actually?
No.
It's CONT, it's a different model than CONT. Okay.
I think so.
Then each black body has a temperature and CONT has a temperature. So which case is that KT? I got confused when
so
what are you comparing here? exactly?
So here the color shows us the preferred models. So for this one, for example, so blue color means that the MDB, RCS, and PONT model preferred for this time segment.
Okay.
So, but all
I'm
these
asking
showing the
where is the temperature coming from? Is it coming from the MBB model or the COMT model?
so PONT model result is here. We have the for PONT model we have the peak values.
And the model gives only E peak but no temperature
No temperature, peak, and index.
index.
Yeah.
Okay, and KT there is still, for example, then in the BB model with the red, that's two black body models, right?
Yes. So we
Okay,
have
so
two
which
temperatures.
temperature is
This
that?
one is the this shows the high BB temperature. This shows the low temperature. So they are a one model. So we represent the spectra with two temperatures. And for the MBB RCS, we have only one temperature value, like a single black body, but it's modified as we talked. And in the end of the clustering, we obtained 287 spectrally distinctive clusters, and we fit the spectrum of each cluster again with the same three photon models. And again, based on the BIC values, we preferred statistically, we determined the statistically preferred models. And the results are similar to the first step, percentage-wise. PONT is still the most preferred model nearly by all spectra, but still a significant portion of the spectra is preferred by thermal models as well. And for the preferred model fit results, we also employed a goodness of fit test using CSTAT, and we found that those fits are remaining in the statistically acceptable range. Let's discuss our each model results separately. So for the COMT model results, as we said, it's the most preferred spectrum. Here we observe we see the E peak versus photon index data, and it's color coded based on the energy flux. And for the photon index, if you see the negative values here, they are associated with the lower flux values with the purple color. And also for the highest flux values, the red color, we see that they have a very narrow photon index range.
So it goes from negative to positive, meaning it goes from non-thermal to thermal?
So this is a non-thermal model completely.
Yeah, but how is the photon index positive?
So this
For that matter, I mean, I don't know how they construct the model itself, but the photon index, thermal and non-thermal, switch. So that I did not understand. That maybe it has to do with something that has to do with the model, but there is definitely a huge difference between a -1 photon index and a 1 photon index as far as science and physics is concerned. So that is going to be important, and just a very simplistic thinking. That is a switch between thermal and non-thermal.
So
And as far as I don't know the model well, so I can't help. But if you think about just a simple power model, assuming power law, then that the switch between the power law pair, basically from a positive to a negative index is the difference between thermal and non-thermal emission. However, I don't know what that is for the company. Maybe you can tell us later.
So for the COMT model, we represent the spectra with two parameters, the photon index and E peak. The photon index shows us the slope of the spectra at the beginning, so it can be positive or negative. So we see it represents the lower energy channels, describe the characteristic of the spectra. And for E peaks, when we see the E peak value is where the characteristic decrease in the spectra begins.
So it's kind of a breaking power.
Yes,
So there's
That's
also-
why it can be negative at low, because at low energy, it can be negative as the flux seems to be increasing. So it's a harder spectrum.
yes.
What is the second power line? It's fixed. Maybe it's a broken power line, with two power lines.
Oh no, I was thinking like, it looks like.
Ah,
So there's a power load, then a high energy cutoff kind of break, and then, which is this EP apparently, and then the flux just decreases, right, exponentially.
So this
Yeah.
EP is like actually a couple. And
Yes, yeah, where the cutoff begins. And for EP and for photon index, we can see a correlation with the flux up to a certain flux level. So if you check the purple and blue data points, we see that the photon index is increasing with increasing flux, but then it starts to decrease with increasing flux. So we can say that in the sense there is a first increasing and then decreasing trend. And for the EP flux correlation, we observe a positive correlation. We can observe a positive correlation with flux because as we go up in the EP axis, we see that the color is changing from purple to red. And to quantify this correlation, we calculated the Spearman correlation coefficient and found the correlation as around 0.8, which lends support for the observed correlation.
you applied this, I'm so sorry, I just got confused. Sometimes I forget the beginning of which data were we applying this to?
For the clustering, so at the end of the class,
No,
Magnetar
which detector?
GM.
GBM, it's Fermi, only
Yeah,
Fermi.
yes,
Okay, so this goes up to, this is extremely hard then.
Yeah.
How are you seeing the so very soft energy? Does it seem?
Starts from 8, right?
yes,
Eight.
Eight.
But you can see the black bodies?
Those are magnetar.
Yeah,
Black.
no, I'm just.
Black body, very
Okay.
hard black body, so
Okay.
already the temperatures are
Okay,
very.
so temperatures are. Okay, so I wondered because I saw the 50 keV there, then that's only normal. It's going to see the 50 keV so well, then the break. I mean, it's important that it actually sees the break. too.
Yeah.
The-
so to better quantify these relations, we fit the trend between the EP and flux and between photon index and flux. And to do that, we group the data in flux domain and obtain the weighted mean representation of the data. Here, the black points show the weighted means. And we found that this EP flux relation, for this EP flux relation, the best fit is a broken power law model. And the relation is always positively correlated, but we see that the slope becomes steeper after the break. For the photon index and flux, we have, as we said, we have an increasing and then decreasing trend. So by fitting, so we see this relation better. And also, for these both trends, the breaks are consistent with each other. So they are at the flux of 2 times 10 to minus 5 Earth per second per centimeter square. And we compared our results with SGR 1550 because it's another prolific magnetar that we can study their bursts, and there is a nicely performed time-zone spectroscopy by Yunus et al. And they also found that this EP flux relation can be described better with a broken power law. And the breakpoints are at the same order of magnitude, and also there is another source, SGR 0501, performed, they also, Lin et al., they also performed checked the EP versus flux relation and found the breakpoint around a similar value. But this may be a pure coincidence because considering their distances, this may be a coincidence.
Their relation is so far. Their relation is so flat. From Einstein's flat. It's very flat. That compared to your relation, you are seeing much more evolution compared to what they are.
Yes.
Which was in peak is concerned. And the index.
The scale
The
is
name is-
logarithmic on the left hand.
Yeah.
I can see the scale
It's
slower.
logarithmic, so that maybe
Oh, it's logarithmic.
Yeah.
Ah, okay, so that's linear and that's logarithmic. Okay, okay. Okay, so that means, and that's also here the same thing? That goes.
the right, no, it's-
Yeah, it's
That's-
similar. Yeah, the values are similar now. Yeah, okay. It's the scale that are. Okay, sorry.
Can you explain what the photon is?
The photon index is for the spectrum. So with photon index, we define the low energies of the spectral index. So if we have an spectra like increasing from low energies to high energies, we have a positive photon index. So it's a sign, kind of defining the shape of the spectra. So if it is positive, it means that like this. But if it is negative, this means that so the number of low photons is higher at the beginning, then starts to decrease, and the characteristic the peak cutoff relation. Or if we have a positive photon index, this means that the number of photons are increasing at the beginning through the high energies, then there will be a cutoff.
Other classifications.
So the cutoff E peak is either in the low energies or high energies, and that changes the index that you see in the spectrum. Right, so if the cutoff is in the higher energy, you have a positive index. The cutoff is in the lower energies, you see a negative.
I think it doesn't have to be like that. It can be, but maybe it cannot be. It's possible. Both ways are
Yeah. But this is a quantized cloud model, right? The COMT.
Yeah, it's so there are some models called TT or
There are
Cloud
several of these, yes, but this is a quantized cloud model.
yeah.
They just have different parameters.
So for HGR 1550, we have they found a negative correlation between the E peak and flux value till the flux breakpoint. On the other hand, we always see a positive correlation. And for the photon index and flux relation for HGR 1550, the photon index remains constant till the break, then starts to increase, but we have a very different trend than the 1550. And let's continue with the BB plus BB model results. So for BB plus BB model here, we have two parameters for this model, the KT low and the KT high. And we also again color coded this based on energy flux. And we can observe a positive correlation between these two parameters. And we found the correlation coefficient as around 0.7. And in the time integrated studies of the same bursts before performed by LIB, so there was no correlation in the time integrated spectral analysis, but in the time result case, so we saw a correlation between these two parameters. And if we check the energetics, so we see that for the low flux values, the blue and purple data points correspond to lower temperatures, but the red and yellow color, the high flux values, can be represented with higher temperatures, and the intermediate flux values, the green color, have a much wider temperature range from very top to very bottom. And we also calculated the black body emitting areas for these temperatures and obtained the R carrier versus KT relation. And we divided our data into 4 flux ranges. And we found flux-dependent variations in the R carrier KT relation. So if we see the lowest flux group, the blue color, we see that this relation can be both statistically prefer both power law and broken power law models. But for the higher flux values, we see the broken power law relations. And but if we,
I'm a little bit confused here. You're looking into R squared, this is the R of the neutron star.
the area of the emitting black
Within
body.
the black body.
Yeah.
Okay, so and you're talking about there the quantization with the breaks. So these are basically composite models where you have the BB plus something else.
This is only BB plus BB model. So for this model, we have 2 parameters. So we define the burst as with 2 hotspots, one near the clouds and one at the higher altitude with larger areas. For the
And this plot doesn't show the spots with different colors, I mean different temperatures.
so here we have the temperature versus R square versus KT relation. These colors are for flux. So for
Different flux, different
Yeah.
time. Okay, I'm asking, you have 2 black bodies, 2 temperatures.
yes,
Where are they?
so these are the low KTs and their corresponding areas. So and these are the high KTs and their corresponding areas.
Okay, so here
Second
you
black.
have a continuous temperature distribution where you either it's from the first spot or the second spot.
Mhm.
Okay, but it could be of but see okay, these are of the same flux level, but and of the same spectra actually, the color coding.
Okay, so for
Okay,
color,
okay, I'm trying to understand because you just distributed all the temperatures as a soup, okay, and but then each temperature, each spectra has a high and low temperature. And I'm wondering if that high and low temperature of each spectra are represented with a single color.
yes,
Okay.
so it's the overall flux of the burst of the
Okay.
emission.
Okay. But there's no switch of some flux differences because of black body. Okay.
So if we check only the blue color, if the low KT is here, their corresponding high KT is here as well.
Okay.
What about the normalization of these 2 models? Were they comparable? So they were both effective?
That's the R square. So you have for one spectrum, you have 2 points in this plot. One in the lower right, one in the lower upper left. And then if there is so there are 2 temperatures, 2 emitting areas for one X-ray spectrum at blue, let's say, flux level. So if you count the blues, you understand it. 1, 2, 3, 5 above, 5 below this break. So that's the lower black bodies, lower temperature black bodies, and that's the higher temperature black bodies.
But then,
So you said these are 2 hotspots, but I mean the radii are pretty big. So I mean, it looks more like one is the surface than your hotspot.
This one, the high KT is near the surface, near the crust, and this low KT is at very high altitudes in the magnetosphere.
So the assumption is that there is some plasma trapped in the magnetic field that seems to be emitting kind of like a black body. Then
Thanks for the help, Hocam. So, the overall trend in all flux groups are similar. We observe negative R-KT relation in all flux groups, but the relation becomes steeper after the breaks of the broken parallels. And we can explain these relations with the special extension of active emission region. We can assume a broad flaring flux tube from the crust to higher altitudes. And gas in the emission region will cool naturally while moving from the hotter, smaller region near the crust to large area high altitude regions. And the magnetospheric simulations showed us that the radiation is quite isotropic near the crust. And this actually consistent with our findings because for this high KT relation near the surface, we found that these indices are not deviate from the Stefan Boltzmann law much. They are consistent with the isotropic radiation. And at the high altitudes, the radiation becomes significantly anisotropic, and this can decrease the intensity at these high altitudes, and such a decrease can lower the perceived area that we observe. And this creates the breaks that we observed here. So since the perceived area is lowered, so this breaks the relation and the best fit becomes broken parallel. And if we compare our results with SGR 1550, again, we saw they also used the same flux values. We divided into 4 flux groups since they did such analysis and used these flux values. So we can directly compare both sources. And we found that these two studies are consistent with one another in all flux groups. They have a similar R square versus KT relation. So the relation is negative, but becomes steeper for the R square KT high relation.
Excuse me. The device is more effective after 8 kilo electrons, right? And so should it be that there's this breaking just because it's not as effective with the 3 to 8 kilo electron volts?
So you mean how?
Yeah, the break, could it be that it's not as efficient as the performance beyond 8 kilo electron volts?
Maybe, but so I think there were a study done before. So they are using the low, including the lower energies as well. And so you have a much wider energy range. And if we fit by using that wider range and only the GVR starting from 8 kV, I think they found the results consistent.
Same, right?
Yes. So I think even if we include go to the lower range, I think we will obtain these temperatures.
One question that I'm a little bit stuck at the fact that you have 2 different plasmas who are doing basically work. They're basically sort of comprised or made with different mechanisms. One is kind of in the magnetosphere somewhere, also under the effect of magnetic fields. Oh, well, they're all under, but the different magnetic fields.
Yeah.
One is at the spot, at the surface, and so forth. Now, and I'm really wondering if the sort of structuring and evolution of these 2 spots would be comparable, or maybe they could be comparable, They could intermingle or they may not intermingle. But I would be think that I would think it would be interesting not to look at the flux in, like do a flux classification or a temperature, do a temperature, separate the temperatures, do a flux distribution instead of temperature distribution. But you've done something like that. You had it, but that wasn't on different temperatures. So what would be very interesting also to see, if you haven't done, separate all the temperatures. Look at their distribution and evolution. Because these two entities, they don't need to co-evolve. Or they could be, some of them could be interfering with one another, or maybe they may not be interfering, since they're completely different entities. First, I was thinking they're just two spots on the surface, but apparently not. So these two entities are very different. So that I'm a bit perplexed that it's interesting to see actually that they can fall in one line like that. Because the flux, the sort of give you some sort of distribution, but still I would imagine their evolution.
How long was this burst? Do you remember?
These are the all the
All of the bursts.
yeah.
But a given burst, how long is it?
The duration might be. Point a little bit longer since these are the right.
A few seconds, right?
A second.
So it is just probably just one spontaneous event happening and pushing towards the temperature in the hotspot and probably the whatever there is this magnetic cloud. So it's probably that's why they seem to that's why they seem to be. It's not a
It's not an
independently
long-term
existing thing.
Even
but
in the tail of the burst.
the whole thing lasts a few seconds, right?
They're not
At
active
most.
below package.
Yes, less than S.
Yeah, so that's why they seem to be in relation to each other.
Interrelated. That would be so interesting to
Yeah.
see if there is anything that comes up, and that could be something specifically important.
And I think there can be modeled with the multi-variable BBs. So you don't have to fit with only two BB, it doesn't have to be two spots, but it's the very basic model to explain the observed emission. And finally, for the MPB RCS model results, we observe a positive correlation between the energy, flux, and temperature, and we found a correlation around 0.6. And on average, we can associate that the lower fluxes can be associated with lower temperatures, again, as in the BBB plus BB model, and high temperatures can be associated with high temperatures. And we also calculated the blackbody emitting area for this model and obtained the R square versus KT relation. And again, we divided our data into flux groups. But for the highest flux regime, the red color, there are only 3 spectra that favors this model. Therefore, we combined these 2 flux groups, and in the end have total 3 fits, 3 trends. And for all of these relations, we found that the best fit is a power law model. And if we see the lowest flux regimes, the power law index is around -4, which as expected from the isotopic radiation, expected from the Stefan-Boltzmann law. But for the highest spectra, we observe a power law index around -2, which is significantly different from the lowest flux regimes and also the isotopic radiation. And the reason can be for this highly energetic events, multiple scattering of photons by magnetospheric particles are possible. So we say in the ABB RCS model, the photons escape to infinity after just one scattering, but for a highly energetic events, this may be not the case, so we may need the multiple scatterings, and this model should allow these multiple scatterings. So the 1/3 of our spectra is preferred by this model, so our results encouraging the further employment of the model, but also shows the necessity for the improvement for the model. And you can find the paper in archive. Thanks for looking.
Any additional questions?
So when you had the 90% in the types of spectra, you had just left, okay, here, Comte. How many of this was the composite? Composite?
What do you mean by that?
BB plus Comte.
We don't know. We don't have such. Each of them are
Are separate. No composite.
Yeah.
No composite.
Yeah.
Have you tried?
No, we didn't. Because for magnetite spectra, we know that these are the best ones.
I don't know. When I say composite, it could be black with the plastic composite.
We didn't try, and I don't know whether it's appropriate to our spectra. I didn't see such an application before for the short magnetite.
So I in the very first slide you had the times when they were actually, these models were sort of dominating that there. So BBs are at the very end or somewhere like near the peak, at the peak, and you have either BB or Comte in the green.
So we can close this one, this middle one. So these two show the BB plus BB model preferences for all of the bursts. But color code shows the preferences. So these are all the parameters of the BB plus BB model. Just so, for example, here, BB plus BB model is not preferred actually, but we have results. And we know that these code parameters describe the data well, better than the BB plus BB, but still we have the fit results for the time segment.
Okay.
So you can, these
Okay.
are parallel. So for red ones, only BB is preferred. For example, here we do not check this one, maybe this one.
Okay. So that's what I was thinking when I looked into that. I mean, that's KP versus time. So okay, so at that particular time, only the red one at the center, BB plus BB is the best fit.
Yes.
Okay, so after that, the green meaning either BB plus or Comte.
Yes.
That's what I was asking.
Yeah.
And at the very end, the best fitting model is BB.
These red
At the
ones.
red one.
Yes.
At the very end.
Yeah.
Okay, and at the very beginning, the MBB RC
Or
model
Comte.
or the Comte
Yeah.
model works the best. Okay, this is what I was asking. Okay, so there seems to be some form of evolution here. I think in that sort of, have you it's in your papers, have you interpreted that type of some evolutionary sequence, given that what's happening as the bursts are evolving and so forth? Because here it seems like regardless of your flux level, they are doing the same thing. Am I understanding correctly? Because each curve on the bottom is a different flux level,
Yes.
right? Each curve. And each color is the preferred model. So obviously, at the given time, it's always that model, regardless of flux. Am I understanding it incorrectly?
This is one average burst profile. So it's a function of time, right? The gray.
I'm sorry, okay. No, I'm not actually thinking of different, I'm thinking of the same verse.
Huh.
Okay.
Yeah, for a given
Thinking of,
burst.
different than how can it be at different flux levels, then it's not.
The brightness changes. And
The burst frequency. Aynı şey mi?
Nasıl
Yanlış mı?
It's the same burst.
yeah, same word,
Yeah.
but we divide it into pieces, so if
At
you
different
follow-
time scale, time.
But it's the same time.
Yeah, it's just one, this is the whole burst, 1 second, 1.5 seconds.
Okay.
So they divided into, let's say,
Flux level.
no, it's not different flux levels. These upper pluses, crosses show the higher temperature black body. And then there's another black body, the lower crosses. That's the second cooler black body's temperature evolution.
Okay, so
As a
these are
function of
different
time.
action components.
Yeah, there are two black bodies, one hot, one cold, and that's their time evolution.
Okay, same, okay, so different, I got it, so same word, different components. of it.
Yeah. Şu şeyleri kapatayım. Efendim?
And one other question, last question right now. What's the advantage of keeping overlapping spectra?